Hello everybody and welcome to this lesson. Previously we have discussed about facilities location. Under facilities location we have seen about the importance of facilities location, features of facility location, when we need to determine facilities location, when we need to make a decision about facility location, and the other is critical success factors. And today we will discuss about methods of evaluating location. If we have more than one location alternatives, if we can have more than one alternatives, so we need to evaluate those locations. Those techniques are, the first one is factor rating method, load distance method, break-even analysis, center of gravity method, return on investment, and the last one is, that is the sixth one, is transportation model. So using these techniques, using these methods, we can evaluate alternative location in order to make a decision. In order to make a decision, we have to evaluate using these 6 techniques. We will discuss one by one. The first method is factor rating method. In factor rating method, there are steps, and the first step is identifying the important location factor, that is critical success factor. As we have discussed before, there are a lot of critical success factor. So here we need to mention those critical success factor. For example, the economy, innovation, or we can consider the market or purchasing power, supplies, and demand. There are more critical success factors. Anyway, in the first step, we have to mention all the critical success factors. After listing out all the critical success factors, the second step is assign a weight to each critical success factor according to their relative importance. Based on their relative importance, we need to assign weights for those critical success factors that we mentioned in step 1. And the third step is assign each location according to the merits of the location for each critical success factor. With regard to the critical success factor, we have to give a score for each location. We have to give a score for each location based on the critical success factor. Then after that, the fourth step is calculate the rating for each location by multiplying the factor assigned to each location, that we provide in step 3, and the basic factors considered that we assign in step 2. So we multiply the factors assigned in step 2 and step 3. And the fifth one is find the sum of the product. Find the sum of the product that we calculated in step 4. Calculated for each factor and select the best location having the highest. Here is an example. Let us assume that a new medical facility healthcare is to be located in Oromia region. The location factor rating and scores for 2 potential sites are shown in the following table. So, which is the best location based on the factor rating method? The first step, as we see in the previous slide, is mentioning or list down the critical success factor. So the critical success factor for this example is 5, that is facility utilization, total patient per month, average time per emergency trip, land and construction costs. And the last one is employee preferences. These are the critical success factors. And after that, the second step is we assign a weight according to their merit. We assign a weight for each critical success factor according to their merits. So these weights are provided for each critical success factor. Based on these weights, facility utilization gets 8, total patient per month is provided 5, average time per emergency trip is assigned with 6, land and construction cost got 3, and employee preferences get 5. So these are the assigned weights according to their merits. And the third step is assign a score or give a score for each location according to the critical success factor. According to their critical success factor, we provide score for each location. That is location 1 and location 2. So, in terms of facility utilization, here is the overall weight, and the location 1 is gets 3 and location 2 gets 5. And the same is true for the other critical success factor from this weights, as you see. So, the fourth step is multiplying the critical success factor weight, the weight with the score of the location. Multiplying 8 by 3, 5 by 4, 6 by 4, 5 by 3, 5 by 5. And the same is true for location 2. 8 times 5 for location 2, 5 times 3, 6 times 5, 3 times 2, and 5 times 3. And the last step is after we multiply the weights with the score of the locations, with the score of each locations, the last step is adding, as you see from this table, we multiply for location 1 and we multiply for location 2, and the last step is adding those multiplied products, those multiplied outputs. So when we add for location 1, we get 96, and for location 2, we get 106. So 106 is greater than 96, so the best location is location 2. According to these critical success factors, location 2 is better than location 1. Let's add some more example. 2 countries are provided as an alternative location, that is France and Denmark, and the scores out of 100 is also given. For France, the scores out of 100 based on these critical success factors. The critical success factors are labor availability and attitude, people to car ratio, per capita income, tax structure, education, and health. So the weights are also provided. The weights are also provided for each critical success factor according to their merits. And the score for each location is provided from 100. The score for each location based on the critical success factor is provided for each location, and after that we can multiply the weights with the score. The weights for the weights of the critical success factor with the score of the locations. Then this is the result, and we add that product, that multiplied output, and we get the final score. For France, we get 70.4, and for Denmark, we get 60. So 70.4 exceeds 68, thus France is better location for our facility. This is another example. If we have 3 alternative locations, that is A, B, and C, and if these critical success factors are provided with the weights, with these weights, so and these are the scores of the location according to this critical success factor, then we multiply this weight by the scores of each location, and we add, and finally we compare the results. And here in this case, 605 is greater than the other, so location C is better. Location C is best among these alternatives. Now let us move to the second method, that is load distance method. As the name indicates, the load distance method is just calculating the distance between the pointers, and we decide the closest point maybe to the supply or to the demand or to the market. The load distance method is a mathematical model used to evaluate the location based on the proximity factors. It considers proximity, closeness. The objective is to select the locations that minimize the total weighted loads moving into and out of the facility. This assumption is that when we are closer, so the transportation cost will be minimized. So this method, we calculate the distance between 2 points and we choose the closest one. We choose the closest one for our maybe supply, for our maybe market, and so on. There are 2 points here. 2 points are provided. So in order to calculate the distance between 2 points, we just take the difference between x and square and plus the difference between y square and under square root. So we get the distance between the two. If there are some more pointers, so we can calculate like this. And ultimately we choose the closest location. And the third one is locational break-even analysis. This method considers cost volume analysis used for industrial location. And there are 3 steps in this method. First, we have to determine the fixed and the variable cost, that is total cost of each location. We have to determine the fixed cost and the variable cost, that is total cost of each location, and plot the cost for each location. We have to plot on the XY axis the total cost of each location. And the last one is select the location with the lowest total cost for each expected production volume. And if some specific certain volume of production is given, so based on that volume of production, we have to evaluate, we have to select the lowest total cost. Let's see with example. If we get 3 locations and the selling price is given $120, expected volume is 2,000. The expected volume of production is 2,000, and the cities are Jimma, Dase, and Addis Ababa. The fixed cost for each location is provided. For Jimma, 30,000, for Dase, 60,000, and for Addis Ababa, 110,000. And the variable cost for each location is provided like this. For Jimma, $75, for Dase, $45, and for Addis Ababa, $25. Then the total cost, because the volume is provided, so we can calculate the total cost as fixed cost plus variable cost. And variable cost, in order to calculate the total variable cost, we can multiply the expected volume with the per unit cost, the per unit variable cost. So here, the total cost can be calculated as fixed cost times variable cost times volume. The variable costs are this, and the volume is 2,000. So when we calculate the total cost, we get 3 total costs for each location. As we see from the formula, the formula of total cost can be obtained by adding fixed cost plus variable cost times volume. So as the volume of production varies, as the volume, for example, from this graph, we can see that as the volume of production is between, if the volume production is between, that is less than or equal to 400, so the optimum location is C. As you see, the total cost for C is less than A and B. And as the volume of production is between 400 and 1000, so A can be selected. A can be selected because the graph of A, the line of A is below than that of C and B, within this range. And when the production is greater than 1,000, so that is from greater than 1,000, the lowest line is B, so we choose B because the total cost for B is less than A and C. In short, as the volume of production varies, the best plan to be selected, the best location to be selected also varies. It varies with the volume of production, as you see from this graph. With different volume of production, we can select different locations. As you see, because the total cost varies. The fourth method is center of gravity. Center of gravity, the objective of center of gravity method is to minimize or to get the minimum distribution or transportation cost. The main objective of center of gravity method is to minimize the distribution or transportation cost, and it considers location of the market, volume of the goods shipped to those market, that means the capability of the market, and shipping cost or the distance. These are the considerations. Then, these are the steps of center of gravity method. The first one is place existing location on coordinate grid, that is XY axis. On XY axis, we place the existing location. And grid origin and scale is arbitrary. Grid origin, that means we provide arbitrary origin, and maintain the relative distance. We have to maintain the relative distance for when we represent on XY axis. We have to keep in mind that the relative distance should be kept in mind. We have to give the proportion distance. And next, calculate X and Y coordinates for the center of gravity. We have to calculate the X and Y coordinates for the center of gravity. Assume the cost is directly proportional to the distance. This is the main assumption. We have to assume that the cost is directly proportional to the distance. As the cost increases, proportional to the distance, that as the cost increases, the distance, as the distance increases, the cost increases, and as the volume of shipped increases, the cost increases. So both distance and volume shipped increase costs. Let us see with example. If we have four locations, and we represent those locations on XY axis, and we provide an arbitrary origin. This is origin, the XY axis origin. So we provide X and Y component for each location, for each four locations. Then the next step is to find center of gravity. And here we have also given that the frequency of shipment is provided, should be provided. Here is the number of containers or the frequency, the shipped per month. These are the frequency of coming and going for the ships. And these are the coordinates. In order to get the center of gravity for X coordinate, we multiply the X with the frequency, the other location, that is 90 with the frequency, 130 with the frequency, 60 with 2000, that is the frequency. So we take all X of location and we multiply those X's with the frequency and divided by the addition of frequency, summation of frequency, and we get 66.7. And the same is true for getting y coordinate. We multiply with y coordinate with the frequencies. We multiply with y value with the frequencies, and we add, then we divide by the summation of the frequency, and we get 93.34 y coordinate. So when we plot those 66.7 and 93.3, that is the centroid, that is the center of gravity. As you see, here is the center of gravity. And when you see there is high frequency, it shows that there is high frequency in Pittsburgh, and there may be less frequency in Chicago. This center of gravity indicates that there is high frequency in Pittsburgh, maybe less frequency in Atlanta. Let's come with return on investment. Return on investment compares the locations according to their return. According to their return for the expenses. There are expenses, initial investment or total expected sales or distribution expense. There are expenses, and lastly we get revenue. So according to that return on investment, we decide the best location with a maximum return on investment. Let's see this example. From the following data, select the most advantageous location for setting a plant for making transistor radios. These are the expenses. For each location. Site X, Site Y, Site Z. As you see, there are some intangible costs, that is community attitude, here indifferent, want business excellence, this one, and here indifference, employee housing facility. Site X is poor, whereas Site Y is excellent and Site Z is good. So if we get equal value with the tangible costs, so we can compare with these intangible costs. And the total expense for X is 195,000, for Site Y is 215,000, and Site Z is 235,000. Let's calculate the return on investment for each location. A rate of return on investment can be calculated by total sale minus total expense divided by total investment times 100. We take total sales and total expense from the previous slide, and we get 27.5 for Site X, 42.5 for Site Y, and 7.5 for Site Z. So based on this calculation, location Y can be selected because there is higher rate of return in that location, that is 42.5, which is greater than X and Z. Coming to the last method, that is transportation model. Here, transportation problem is a special type of linear programming problem where the objective is to minimize the cost of distributing a product. Just like that of the center of gravity method, the objective is to minimize the cost of distributing a product from a number of sources or origins to a number of destinations. The problem of finding the minimum cost of distribution of a given commodity. The problem of finding the minimum cost distribution of a given commodity. We have to find the minimum cost. There are two phases when we calculate the minimum cost using transportation model, there are two stages. That is, phase 1 obtains the initial basic feasible solution using northwest corner cell method, least cost cell method, or VAM method. And after that, after getting the initial basic feasible solution, so we further calculate the optimal basic solution. We further calculate in phase 2, we have to obtain the optimal basic solution with UV method. Let's calculate it. Let's take this example. These are the supply side. We have three sites for our supplies. We have 3 sites, and we have 4 demand sites. Find the initial basic feasible solution of the following transportation program by northwest corner cell method, and then optimize the solution using UV method. These are the supplies. We have 3 supplies, and we have 4 demands. As you see, when we express this graphical representation with table, these are, in order to take our supply to the demand side, we have to incur 3. The cost is 3. The cost between S1 and D2 is 1. The cost between S1 and D3 is 7. This number indicates the cost of transportation. The cost of transportation between the supply and demand side. And these are the capacity for the supplies. The capacity for supply S1 is 250, as you see. For S2, it is 350. This is 350, and for S3 supplies 400. And the demand is for D1 is 200, for D2 is 300, for D3 is 350, and for D4 is 150. And this is the sum of the capacity, the sum of the supply, and the sum of the demand. And this table indicates that it is a balanced transportation problem. Because the sum of the demand equals the sum of the supply. Sum of this demand equals sum of these supplies. Which is 1000. Let's move on. Using the northwest corner, that means phase 1 corner cell method, we have to get the initial basic feasible solution. This cell is the northwest corner cell. It is north and it is west corner cell. And from that cell, the corresponding points for D1 is 200, and the corresponding for S1 is 250. Among those corresponding values, we have to take the minimum one. Minimum of those corresponding values, 250 and 200. So the minimum is 200. So we put 200 in this northwest corner cell. We put 200 in this cell. We put 200 because it is minimum. And in order to remain the same capacity, so in order to maintain the corresponding row value and corresponding column value, so we subtract from 250, we subtract 200. So the result becomes 50. And from here, from 200, we subtract 200, and it becomes 0. And the next north corner cell is this one. So for this cell, the corresponding values are 300 and 550, and minimum of 50 and 300 is 50. So we put 50 here. So when we put 50 here, we just subtract from 50 and the result becomes here 0, and we subtract from 300, we subtract 50 from 300, so the result becomes 250. So we just finished the first row because it becomes 0 here, it becomes 0, so we just finished the first row, and the next we also finished the first column. So the next northwest corner is this point, and the corresponding value is 250 and 350, and we just move this 250 to this, we just move 250 to this, and we subtract from 350, and the remaining here is 100. The remaining here, as you see, it is 100. And we just finished the second column, this column, and the next northwest corner is this one, and the corresponding value for this is 350 and 100. So we move this 100 to this point. When we move this 100, this becomes 0, this cell becomes 0, and we subtract from 350, we subtract 100, so the result is 250 here. We put 250. And we finished the second row, this row, S2 row, because it becomes 0. And the next northwest corner is this point, and the corresponding value for this point is 400 and 250. We move 250 to here, and we subtract 250 from 400, and we get 150. We get 150 here. And this table shows we put 250 here, and we subtract from 400. When we subtract 250 from 400, we get 150. And we finished this third column, and the northwest corner remaining point is this point, and the corresponding value is both 150 and 150. So we move 150 and we make the other 150 0. And the last table looks like this. As you see, these green cells. So as you see, these are the final result, and this is the final initial basic feasible solution. And we multiply this value with the cost, the corresponding cost, and we get the total cost. The total cost is 3,700. Now let's move on to the second stage, that is getting optimal solution. Application of UV method for optimizing the solution. As you see, these are the corresponding cost and this is the value. So we have already calculated the basic feasible solution, the basic feasible initial solution. Using the UV method in order to optimize the solution, we provided V1, V2, V3, and V4 to above the rows, and we provide U1, U2, and U3. And UI plus Vj equals Cij, and Cij is the value of the costs, the cost value, the cost that is 3. For example, C11 is 3, C21. That means this one is the first row, the first column, and this one is the first row, second column. That means C12, and this one is C13, and this one is C14, and this one is C21. That means the first, the second row, and the first column. So using this formula, first, then we have to check that m plus n minus 1 is equal to the allocated cells, that is 6, that is the green cells. M is M represents the row, number of row, and N represents number of column. Number of row plus number of column minus 1 is equal to number of the allocated cells. These are the allocated cells. The green cells are the allocated cells that we get from the first stage. So this is equal. So first we assume that U1 is equal to 0. We provided U1 is equal to 0. U1 is equal to 0. So using this formula, we add U1 with V1. V1 is unknown. U1 is 0. 0 plus V1 equals 3. So V1 is 3. V1 is 3. U1 plus V1 is equal to 3, and V1 result is 3. And U1 plus V2 equals 1. So U1 is 0, so V2 is 1. V2 is 1. So V2 is 1. And second row, second allocated cell, U2 plus V2, that is this one, 6. And V2 is 1, so U2 becomes 5 because V2 here is 1. And the same is true for all the cells. We calculate like this. And after that, after getting all, calculate value of UI plus Vj equals Cij. The second step is calculate the unallocated cells by using Pij equals Cij, that is the cost, the value of the costs, minus UI minus Vj. Because we already calculated Vi and Vj, so we calculate the unallocated cells. Now we calculate the unallocated cells. Unlike the previous calculation, we calculate the unallocated cells. So we get this value. For example, for C13, that is C13 means this one. No, this one, because it is unallocated. This one, C13 equals 7, that is the cost, minus 0, that is this one, and minus V3, that is 7. And the same is true for the remaining unallocated cells. For example, if we take C24, C24 means C2, that means second row, and fourth column, this one. C24 is this one, 9, that is the cost, minus 5, minus 1, and the result is 5. And we calculate it in the same way. And the result for C21 means second row, second row, first column. C21 is this one, and C32 is this one. These two results are negative, which indicates that it is not optimal. It's not optimal. So we have to make this optimal. So the step 1 is select C21 and C23. That indicates it's not optimal. So these are unused to evaluate the improvement index. These unused cells, we use these unused cells to evaluate an improvement index. And the step 2 is trace closed paths via used squares. We have to make a closed square. Start positive sign at unused corner and alternate minus and plus using the used cells. And the fourth step is calculate the improvement index by adding the unit cost. And the last one is repeat the steps if we didn't get the optimum solutions. Now let's see. This is the C21. So we have make this plus and this minus. We move to this and we move upper, that is the used cell, and plus, because we need to alternate the signs, and then we put here minus. After that, we have to compare the two minuses. That is, here there is minus and here there is minus, and 200 is less than 250. 200 is less than 250. So we move this 200 to the unallocated cells. We move this 200 to the unallocated cells. So when we move this 200 to unallocated cells, we have to add with 50 in this cell. We have to subtract, because here there is a minus sign, so we have to subtract 200 from 250, and the result become like this. We add 200 here, we subtract 200 from 250 here, and we add 200 with 50 here, and the result is 250. And we finished this. And the other cell is C32, that is this one. We start plus sign and minus, then plus, then minus, and come to the initial point. And the same is true as we have did in the previous table. And we compare 50 with 250, and the minimum is 50. So we move this 50 to the unallocated cell. When we move this 50 to this, so we subtract from 250, because here minus, there is minus sign. We subtract 50 from 250, and the result is 200 here, and we add 50 to 100 here. The result is 150, and here we just subtract 50 and it becomes 0. And here it becomes 50, and the table looks like this. The table looks like this. And here, this is the final optimal solution. Then after optimization, when we calculate the total costs, that is multiplied the costs with the transportation, multiplied the costs with this value, so we get 2,450. As you see, after optimization, it decreases. The total cost decreases from 3,700 to 2,450. 2,450. And this is the optimal solution. So these are the values, the assigned value, the optimum assigned value. That means S2 provided for D1, S1 provided for D2, S2 provided for D1 and D3, and S3 provided for D2, D3, and D4. So this is all about methods of evaluating alternatives. So if you have any question or comment, you are welcome. Have a good time. Bye.